All right, welcome everyone to our first online mini lecture. I already screwed that up, but we're going to go from here because I don't want to record this more than once and I've just started off. We're going to talk about a couple of things today, primarily these key terms in NMR, so that if you haven't been able to keep up with the lecture, you don't have to worry. At least you'd have some sort of online tool to help you understand the different components of an NMR and then piece it together in your analysis of organic compounds. So, some key terms today are signals, multiplicity, splitting pattern, which is almost similar to multiplicity, but there are some distinct differences, and upfield versus downfield that I'll discuss in this particular lecture. And to highlight these differences, I'm going to compare the structures of 1-propanol and 2-propanol to help us better understand these different components, right? The signal, the multiplicity, splitting pattern, and upfield versus downfield. First off is understanding signals. So signals can be easily defined on your NMR. It's essentially the peaks of your NMR that are defined by either one or more hydrogens residing in a unique environment. And what does that mean? Essentially, if you look at your HNMR, which would be down here, a signal would be some sort of a blip or a peak present that is indicative of a group of hydrogens that are in the same area and feel the same effects of neighboring groups. So the way we would go about that is to first draw out all of the hydrogens present on your molecule. So in 1-propanol, the terminal methyl group has 3 hydrogens on it. The CH2 group obviously has 2. And the closest CH2 group to the OH also has 2. We can do the same for our 2-propanol compound. 3 H's on that end, 1 H over there, and 3 H's on this end. All right, so now we're going to try to define how many signals are coming from each of these compounds, and I'm going to do that using a different color. Now remember that I defined a signal as being hydrogens in a similar environment that produce some sort of noticeable pattern on your NMR. So how I would do about that is find all the hydrogens connected to the same carbon and then look at their immediate environment. See what they're connected to and if that group is present anywhere else on the compound, because that can influence the number of signals you achieve. So here we've got 3 hydrogens connected to the same carbon. They're all connected to the same carbon that is connected to a CH2 group. So all of these hydrogens produce one signal because they reside in a similar environment. All of them are connected to one carbon that is connected to a CH2 group. Now what about the next 2 hydrogens? These H's are also connected to the same carbon, which is connected to a CH3 group and a CH2 that's present nowhere else on this compound. So these 2 hydrogens also produce their own signal. And finally, well, not really finally, but these 2 hydrogens over here are connected to the same carbon, which has an OH projection and a CH2 projection that's nowhere else on the compound. So it's got a unique signal, or a signal is produced by these 2. And then finally, this 1 proton attached to our OH group also produces a signal of its own. I'm going to scroll down for you guys here. So in totality, we have 4 signals produced by 1-propanol. Let's compare and contrast this to 2-propanol. We've got 3 hydrogens here connected to the same carbon, which is connected to an OH group. But if you notice on the other side of the compound, you've got something very similar. 3 hydrogens connected to a carbon that's connected to an OH group. So in fact, these 6 hydrogens all make the same signal. So symmetry plays a really important role in establishing the number of hydrogen signals coming off of a compound in NMR. Now, we can't exclude this unique hydrogen It's connected to a carbon that has an OH and two CH3 projections. And finally, let's use brown. We've got an OH group attached, well, we've got a hydrogen attached to our OH. So again, to summate, we've got 3 signals in this case. So you're already seeing how important of a tool NMR can be in elucidating the structure of these two compounds. They're exactly the same chemical formula, they have exactly the same functional groups, but interestingly enough, the position of the functional group has changed the number of signals emitted from this compound once it's analyzed using NMR. Now, once you've figured out the signals, you can go ahead and understand better the multiplicity. The multiplicity tells you for each signal produced what the immediate hydrogen neighbors are. The number of those neighbors is determined via multiplicity. So, how would you determine the multiplicity for each of the signals? And I'll just draw a line here so that past this line would be multiplicity. The multiplicity for each of these signals is as follows. Let's look at this methyl projection here. These 3 hydrogens produce one signal. To find their multiplicity, you first start off by looking at the carbon they're all connected to. Then you move one carbon away on either side. There's no carbons to the left, but there is a carbon to the right. So we're here now. And then we consider how many hydrogens this carbon has. This carbon has 2 hydrogens present on it, and we utilize the following formula, n+1, where n is equal to the number of neighboring hydrogens. So here we determine for this particular signal, it has only 2 neighboring hydrogens, thus 2 plus 1, you get a multiplicity of 3 for that particular group. So I'm going to denote here that CH3 has a multiplicity of 3. Then you move over. For the green group, or the group I've highlighted in green, we look at the hydrogens and then their immediate carbon, then look at the neighbors and see how many hydrogens are projecting off of its neighbors. You've got 3 on this side and 2 on the other side. You plug it into the formula, so 5 plus 1 is equal to 6, and that's what its multiplicity is. So the CH2, and I'll call this alpha, has a multiplicity of 6. Then we repeat the process. For this hydrogen group over here, you look at the hydrogens, the carbon, and the immediate neighbors. Here you see that it's got 2 neighbors to the side, and here you see it's got 1. However, we do not consider any hydrogen projections that are on oxygen. It's only a carbon-based projection system that we use. So here, if I was trying to find the multiplicity of this signal, I would look at the carbon, and then not look to the right, but look to the left. Consider these 2 hydrogens, right? So this group, CH2 beta, and I'll note that as beta for you guys, has a multiplicity of 3. And then finally, I used orange. This hydrogen on the OH, which I'll denote as OH hydrogen, has a multiplicity of 1, because regarding this, we don't consider its neighbors because it's on an oxygen and not on a carbon. So OH groups are interesting in the fact that they don't follow the conventional standards, and you usually see them as a splitting pattern of just 1. So why don't you take a minute to pause the video and try it out for 2-propanol, see if you can figure out the multiplicity of the signals produced, and then we'll talk about it in just a second. Okay, so let's talk about the answer real quick. Here, this is one signal. These 3 hydrogens and these 3 hydrogens together produce one signal. So we have to think about their neighbors cumulatively. So if you look at their carbons and then move 1 away from that. This carbon has 1 H projection, So these CH3 groups are going to have a multiplicity of 2. Your hydrogen here in green will have a multiplicity of 7. And finally, your OH hydrogen has a multiplicity of 1, as we discussed in the previous question. So already you can see a greater difference in the types of data you'd receive from these two compounds if you were to analyze them through NMR. But what does multiplicity actually tell us other than the neighboring compounds? Well, it gives us a way of understanding what we call the splitting pattern that I've mentioned over here. The splitting pattern is what we see when we look at an NMR. It's the pattern of the peak observed. So there are several different kinds of splitting patterns, but they can be as follows. A multiplicity of 1 has a splitting pattern known as a singlet. Multiplicity pattern of 2 is a doublet. 3, triplet. 4, quartet. 5, quintet. 6, sextet. 7, heptet, and so on and so on. Now, what do these look like? A singlet, as you can already tell, is a peak with just one, or is just a singular peak. A doublet is 2 peaks together. A triplet is 3 peaks. A quartet, 4 peaks, and so on and so forth. Again, if you can tell the splitting pattern of a compound, you can directly know how many neighbors a particular signal has. So if I were to say I see a quartet appear in my NMR, I can say, well, a quartet means that I have a multiplicity of a value 4. If that's the multiplicity, then I have to have 3 neighboring hydrogens to my specific signal group. And we can do that over here and analyze it in this way. So this signal produced by these hydrogens will have a triplet signal produced. What that would mean is that this group has 2 neighbors, right, as we can see by CH2 alpha. For this group, the CH2 alpha group, the splitting pattern is a sextet. That means it has 5 neighbors, 3 from the methyl and 2 from the CH2, and so on and so forth. So you can use these tools to better analyze an NMR. Finally, we can talk about integration number and the upfield, downfield nature, and put it all together in our spectrum over here at the bottom to highlight the differences. So the first thing I want to talk about is the integration value. The integration value is a number of hydrogen value you'd see at the top of your peak that tells you about the number of hydrogens in the signal. In certain cases it's given to you, in certain cases you'll have to calculate it yourself, but for example, how would I read an NMR peak that looks like this? In this particular example, I need to consider multiple things. The shape, so I'll write this down for you guys. The integration value, the shape of the signal, and the multiplicity as determined by the shape. The integration value or integration number is this number right here. It tells you about how many hydrogens are producing that particular signal. So in this case, this signal is produced by only 2 hydrogens. That means these 2 hydrogens have the same environment. The shape tells you about the splitting pattern. So here we have 1, 2, 3, 4 peaks together. That means it's a quartet. And the quartet tells you about your multiplicity number. So quartet means a value of 4 for your multiplicity. That means there are 3 hydrogen neighbors to this particular signal, which could mean that these 2 H's are producing our signal, and they're right next to a CH3 group. And that makes sense, right? These 2 hydrogens are making a quartet peak. They have the same environment. That's why they both produce the same signal. That's why we have 2 hydrogens. The quartet is formed by looking at the neighboring hydrogens to this signal and summing them together, adding 1. So we have 3 hydrogens as neighbors, plus 1 gives us 4, a quartet, which is the splitting pattern we observe. And finally, how would I put this all together in terms of an NMR peak? Well, here I can see that I've got, let's write this down, I've got a triplet, right, produced from this peak. I've got a sextet, so bear with me as I draw this out very oddly. That's a sextet. We've got a triplet again, and then we've got a singlet. So I'm just drawing out the peaks that you'd find. Now, I'm going to put them on the graph and show you the differences between 1 propanol and 2 propanol. So this has a integration value of 3. This has an integration value of 2, integration value of 2, integration value of 1. So upfield in an NMR is the rightmost corner of where you begin. These protons are shielded from electronic effects. They don't experience any electron density, so they appear relatively lower in our parts per million. Downfield is where you find protons that are experiencing interesting electronic effects because they're close to some electronegative group, or they're on a portion of the compound that's resonating, right? It's undergoing resonance transformations. So here we see our methyl group is farthest away from our OH, a group that induces quite a bit of downstream movement in our NMR. So this group is going to be right at the end here as our triplet. We're going to have these 2 methyl groups slightly closer downfield, and that's because they're in closer proximity to our OH. And then finally, these 2 H's are heavily downfield because of their proximity to OH. And then the actual H from the hydroxyl group can appear anywhere on your spectrum at any intensity. The important thing is that you'll see it's 1H and has a singlet. Let's compare and contrast this to our 2-propanol group. Here we're going to have a doublet of 6 hydrogen integration value. You're going to have a septet, which is 1 big blurb, 2 smaller ones, 2 even smaller ones, and then 2. A septet with an integration value of 1 hydrogen, and then a singlet with an integration value of 1. The 2 H's are 1 carbon away, so they're going to be relatively low down or relatively upfield. The 1 hydrogen is connected to a carbon directly connected to an OH group, so it's going to be upfield. And remember that it has a septet splitting pattern. And our 1 hydrogen peak can be located anywhere because it's attached to the hydroxyl group. So take a look at it. There's quite a bit of difference between these two compounds, but you can use all this information to elucidate the final product structure. If you have any questions, feel free to email me. I will be uploading possibly another video on how to use this method and work backwards from an NMR to the structure of a compound.